that kind of come together. So we'll start off with some basic questions. We will move into some more challenging ones. And, you know, for anyone, and this brings up another good point, for anyone who's using our curriculum right now for the first time or using a trial, you know, things at first may seem pretty overwhelming, but, you know, the reality is what we have in this quant curriculum is everything you would potentially need to be successful. And if there's certain things you feel like you already know, you know, certainly you don't have to dive in as deeply to those topics, you know, as you would other things that you don't know. And, you know, the one thing I've seen with all my students is that everyone eventually hits a tipping point. If at first things seem like they're pretty overwhelming, you know, stick with it. You will get better. You will improve. You just got to really stay focused and, you know, follow the course. We obviously have a great study plan that you can follow, and hopefully you have been. And as always, myself and Scott, we're always around for questions or comments or anything. So, you know, feel free to reach out to both of us. So with that said, what I'm going to do is put up the first question, give everyone about 2 minutes. This one's pretty basic. It's just a basic LCM question, least common multiple. So if you get the answer quick, that's fine. Just put everything into the chat box so I know what answers you're getting, and I know that people are also done with the problem, and then we can of course go through it. So the first one is this here. Okay, so that was about 2 minutes there. Now, a question like this, anytime you're asked for least common multiple or greatest common factor, you know, and it's this straightforward, there are many different ways you can kind of go about it. I mean, certainly you can look through your answer choices and you can, you know, or first look at the multiples of, you know, 15 and 18 and 24 and, you know, basically go through the iterations of those multiples. Now, unfortunately, 15, 18, 24, they're not tiny numbers. So my thought is it would take a decent amount of time to do that. So the good news is you can be armed with a way to deal with this every single time. And the way that we like to deal with least common multiple questions is we first break them down into primes. So we have 15, 18, 24. This is a 5 and a 3. 18 breaks down to 3 to the 2 times 2 to the 1. And 24 breaks down to 2 to the 3 times 3 to the 1. And, you know, this brings up another point. you know, having prime numbers, not prime numbers, but having certain exponents memorized, you know, certainly when I broke down 24, I could have said 8 and 3, 2 and 4, 2 and 2. But what we can see is that takes a decent amount of time. So if you know that 8 simply equals 2 to the third, notice how much quicker it's going to be when you break down 24. So these are small things that, you know, aren't going to be the bulk of any question, but certainly are going to help you save a lot of time as you're moving forward through the GMAT. So what we do now is we focus in on these primes, and we literally take the largest primes, the largest quantity of all of our primes. So we can start with the base of 2. You'll notice that we have a 2 to the 1 and a 2 to the 3. So we take the larger one, which is 2 to the 3. You'll notice next that we have 2 3s to the 1, so we don't have to take a larger one. We simply just have to take one of them. And then finally, there's a 5 to the 1. There's nothing to compare it to, so certainly the largest 5 is 5 to the 1. Then to get the LCM, we multiply all of these together, and this is where we end up with 360, answer D. So hopefully you'll be lucky enough to see something like this on the GMAT. Certainly there's no guarantee you will, but I can tell you this is a question I'd love to see. Now, the next thing I want to do is kind of do a little least common multiple in a bit of a backwards way, which you'll see in this question. And once again, I'm going to kind of go through 2 super efficient methods in dealing with this. Give everyone another 2 minutes, and again, put everything into the chat box. Okay, so that was about 2 minutes again, and this was a fairly basic question. And actually, before we do the solution here, I want to go back to something that I miswrote in this question. I said that there are 2 3s to the 1. And I was wrong about that. There's actually a 3 to the 1, and there's also a 3 to the 2 in this question, which I will write in green. And as you'll notice, 3 to the 2 is the bigger base, or the largest quantity of 3's here, which means that the LCM is going to be 5 times 2 to the 3rd times 3 to the 2. That equals 360. So if anyone has any questions about this, let me know, but I think everyone understood what we did here. So, getting back to this question here, this is interesting because it has some elements of what we just did, but in this case, we're actually given the least common multiple. So there's two ways of doing this. The first way is a little bit more long-winded and a little bit more technical, but it's worth everyone seeing here. So we know that we have an 8, a 10, and an X. We know that the LCM becomes 120. So if we break these into primes, this gives us 2 to the 3. 10 gives us 2 to the 1, a 5 to the 1, and then there's an X. And then as far as the LCM is concerned, we end up with a 12 and 10, which breaks us down to 2 squared and 3. So we'll actually do this over here. So we have the room. So 120 is 12 times 10. And if we break this down, obviously we have a 2 and a 5 there, a 2 squared and a 3 here. So the LCM breaks down to 2 to the 3rd, 3 to the 1, 5 to the 1. So what we should notice here is that we have certain prime factors already accounted for. So the 2 to the 3 is accounted for. We have the 2 to the 3 stemming from the 8. The 5 to the 1 that's in the LCM is accounted for. So the only thing that we are missing is the 3 to the 1. So what we know is that X must contain a 3 to the 1. Now, it doesn't mean that X has to be 3, and that's where a lot of students have gone wrong in this question. It just means it has to have a 3 to the 1, and it could have other things. But it can't have anything that's not a part of the LCM. So it can't have more than 3 2's, it can't have more than 1 5, and it can't have more than 1 3. So the other thing to be really careful of is anytime you see the word except, that's possible. I've seen students miss that, so they go to a value of X that does work. So knowing that we're looking for anything that works except, well, we can start going through our answer choices. Obviously, X can be 3, so that's out. 6 is 3 to the 1 times 2 to the 1, so that contains a 3. 9 is 3 to the 2. So that's one too many 3's, and in fact, if X was 3 to the 2, the LCM would be 360 and not 120. So we can say this is our answer choice. 12 is 2 squared times 3 to the 1, so that was good. 15 is 3 times 5, so that was good. So basically, that is a technical way to get through the problem. Now, I'm going to wipe the screen clear here of my writing, and I just want to go over one other way that you could see this. So we know that the number 8, the number 10, and some number X have to produce an LCM of 120. Well, 120 is what's called, and I'll repeat it again, the least common multiple of those numbers. Well, what does that mean? It means those numbers must be able to divide into 120. So that means that 8 divides into 120, which we know, 10 divides into 120, which we know, and X also has to divide into 120. So if you look at your answer choices, we know 3 goes into 120, 6 goes into 120, 12 goes into 120, and 15 does, leaving us with 9 as the sole answer. From my standpoint, I wouldn't care how you were to solve this. I think understanding how LCM works, being able to break things into primes, all important stuff. And, you know, the more tools you have in your toolbox, the better off you're going to be in these situations. So with that said, let's move on to a data sufficiency, least common multiple question. This is definitely a pretty challenging question, but if you're thorough, you will be okay here, and as long as you're answering the right question, you will be okay here. So take a stab at this, and I'll give everyone about 2.5 minutes to 3 minutes on this one, but enter your answer in the chat box as you're working through it. Okay, so I see we have a lot of different answers here, which I like. This is a really challenging question. It's a pretty cool question. I was pretty happy with myself when I made it. a few years ago, and it challenges you in so many different places. For starters, you'll notice this is not a question just saying what is n. I mean, the fact is this question could have said if n is a positive integer, what's the value of n, and then that we could have had those two statements. So it's an added element to say what is the LCM of n, 6, and 15. So one of the things to always make sure you're doing is you need to make sure you're answering the question and how it's presented, not how you're seeing it. And sometimes it's easy to, basically, add another added element to the question. So let's go through statement 1. So statement 1 says the least common multiple of n and 8 is 40. So we have an n, and then we have a 40, or an 8, sorry, which is 2 to the third. And then 40 breaks down to 2 to the third times 5 to the 1. So what's interesting about this question now is I'm sure most of you said right off the bat, oh, n can be 5. Now, if n is 5, then we would be done here and statement 1 would be sufficient and we'd move on to statement 2. But where we really have to watch ourselves is we have to say, well, can n be anything else? And n can be. And that's where an answer choice of D or E, or excuse me, an answer choice of D here, or even statement 1 being sufficient, you're going to see that statement 1 is not necessarily sufficient. And let's go back to what we know about least common multiple. Well, we know that we have a 2 to the 3 accounted for here. And we have a 2 to the 3 accounted for here. So that means n at a bare minimum has to contain a 5 to the 1. But it doesn't mean n has to be 5 to the 1. And I think that's where some of you got confused if you said answer choice D. Because remember, n can be 5 to the 1 times 2 to the 1. N can be 5 to the 1 times 2 to the 2. And finally, n can be 5 to the 1 times 2 to the 3. All these are options. Now, of course, that makes this 10. That makes this 20. And that makes this 40. Now, keep in mind, too, if you didn't want to get into primes, you could have very easily looked at, a value of n coupled with 8 and saying that the LCM is 40. And it's quite possible you would have picked out the values of 10, 20, and 40 as other potential values for n. And that's okay, too. Like I said, doing it in this prime factorization manner is probably the most technical. So it depends on how comfortable you feel you are with these numbers and how comfortable you feel you are with this process. But then you see we're not done because we have to make sure that these different values of n are going to give us different LCMs of n, 6, and 15. So if we break these down, you have a 3 and a 2, a 3 and a 5, and then your n. So if n is 5, the LCM of these is going to be 30. Now, what's interesting is if n is 10, because we're not introducing any larger quantities of primes, the LCM of 10, 6, and 15 is still 30. So if you stopped at 10, you would have thought that statement 1 was sufficient. So let's move on to 20, and you can see the LCM with 20 is going to be different because we have an extra 2, so it's going to be 60. Okay, so now let's move to statement 2 here. Statement 2 is very similar. It's telling us that we have an LCM, so we'll just put an X there. We're told that in statement 2, the LCM of n and 12, which is n and a 2 to the 2 times 3 to the 1, is going to give us an LCM that is 60, which breaks down to 2 to the 2, 3 to the 1, 5 to the 1. So with that in mind, we're going to do the same thing here. We notice that we have a 3 to the 1 accounted for. We have a 2 to the 2 accounted for, but again, we don't have the 5. So n at a bare minimum is 5. And once again, if you just said n was 5 and it's nothing else, yes, you would have thought that this statement was sufficient, and immediately you would have said that the answer is D. So we know one option is that n is 5, and if we kind of go in a similar fashion, we're going to see that n can also be a 5 times a 2 to the 1. N can be a 5 to the 1 times a 2 to the 2. If we do these out, obviously we get 10. Here we get 20. And the reality is we could keep going, but if we are being strategic and we are focused on the fact that this is a time exam, my thought is that the minute you see that you come up with n being 5 and n being 20, and you see that that matches this and this, you know that when n is 20, it produces a different LCM of n6 and 15 than when it does when it's 5. And we prove that with statement 1. So what you're doing is you're taking knowledge you used in statement 1, you're carrying it over to statement 2 once you have selected these numbers, and you can say right away that the answer is E. There's absolutely no reason in a problem like this to go to E, because we've determined that statements 1 and 2 are telling us similar information. And although this problem seems long, if we can kind of use those strategies to our advantage by not having to look at these two things together because we know immediately that it's E, you're going to cut down on time there. Now keep in mind, if this was at least a little confusing, this is a very tough problem. There's a lot of components to it, a lot of steps. It is something that eventually I'm sure all of you will be able to do, but it's not the end of the world if right now you're seeing this as a very challenging question. So the next thing I want to do is I want to get into greatest common factor so we can kind of bring together the idea of greatest common factor and least common multiple and talk about some rules with them. So the first thing we're going to do here is put a problem up that's just GCF, so it'll be pretty quick. I'm sure most of you will be able to do it within a minute. We'll go through it, and then we'll talk about a couple more greatest common factor things. So I'll give everyone about a minute to work through this. Okay, so this one wasn't too bad. This is just saying what's the greatest common factor of 60 and 72. What that means is what's the largest number that divides into 60 and 72. So I'm sure most of you, just from the answer choices alone, were able to determine that E was the answer. If we are getting technical here, there is a prime factorization route we can take. So 60 breaks down to 2 to the 2, 3 to the 1, 5 to the 1. 72 breaks down to 2 to the 3 times 3 to the 2. So for the GCF, what we're doing is we're taking the smaller quantities of only the repeated prime factors. So before in the LCM, we were taking the higher quantities of everything. But now we're only taking the smaller quantities of the repeats. We'll notice that 3 and 2 both repeat. The smaller of the 2's is 2 to the 2. Smaller of the 3's is 3 to the 1. So as you can see, the GCF is that. Now, could you have something this straightforward on the test? I mean, yeah, you could, because there are basic questions that are asked. I mean, the GMAT can't just ask you ridiculously hard questions at all times. But I think more so, be prepared to use GCF in other ways, possibly word problems, possibly combined with LCM, which we'll get at, and possibly in questions similar to this data sufficiency question that I'm going to give you right now. After that, we're going to do some GCF and LCM rules. So let's talk about this here. I'll give it about a minute or two, and then we'll talk about it. Okay, so I see most of you who entered in your answer, I think everyone actually got the correct answer here. So the answer here is A. No one said E. E could potentially be a trap here. One thing to note about data sufficiency is that if a question appears like it's really giving you nothing to work with, chances are the answer is not going to be E. And this seems like a pretty vague question, but it actually is giving some really important information about M and M. And what we know from statement 1 is that M and N are consecutive integers. And that's really important because what you'll notice about two consecutive integers, whether it's this, whether it's, this, they don't share any of the same prime factors ever. And it's a cool rule because it can be tested in a lot of different ways. And in this case, it's being tested in relation to greatest common factor. And what we know about greatest common factor is when you get the greatest common factor, you're taking the repeats, or excuse me, the lower quantities of the repeated primes. But as I said, two consecutive integers will never have repeated primes. So the GCF of anything like this is always going to be 1. Of course, statement 2, that's kind of a throwaway statement, n being greater than m. Of course, we even know that from statement 1, but it doesn't tell us that they're consecutive. So the answer here is A. If you had trouble seeing that, my suggestion is plug in real values right away, and you'll see by testing a few sets of consecutive integers that you'll be able to easily get this right. Now, a question is about whether or not this is a value question. This is a value question, so you must get one definitive value when answering this. So when it says, what is the greatest common factor of m and m, it's not asking if you can actually get it. It's asking for what it is from a standpoint of an actual numerical value. So the fact is, we have determined that the GCF is always 1. If for some reason we were able to get that the GCF could be 1 or, I don't know, 10, then statement 1 would not have been sufficient because we would have had 2 values as opposed to 1 value. Okay, so what we're going to do now is kind of mix it up a little, throw some pretty high level stuff at you, but the beauty of this, of number properties is, and the GMAT in general, is that when you know a lot of these rules, all of a sudden something that's 700 level really isn't 700 level anymore. So let's everyone take a stab at this, and then we can talk about it. Okay, so I see we have some answers here, a bunch of C's. Now, this is a pretty cool question, and what's great is, which I'm pretty pumped to see, is pretty much everyone here is getting the right answer. So, unless anyone needs me to explain why this rule works, we can go ahead and pretty much confirm that, basically why this works. But I'm just going to say that the LCM of the LCM of P and Q in this case times the GCF of PQ actually equals P times Q. Now, as I said, if anyone has any questions about that, we can go and do it in further detail, but this is a hard and fast rule. It doesn't mean we know P, it doesn't mean we know Q, but we do know the product of P and Q. So with that said, the answer here is C, and yes, I can explain it. So I want to do a proof with everyone, and the proof is going to be this. I want everyone to give me the LCM 24 and 30, and I want everyone to give me the GCF of 24 and 30. And when I'm done when we have that, we're going to go through and use some real numbers here. So once you get the LCM and GCF, just put that into the chat box. And I will go ahead and sneak ahead here. The LCM of 24 and 30 is 120, and the greatest common factor of 24 and 30 is 6. So what's interesting here, if we take what we call the GCF of 24 and 30 times the LCM of 24 and 30, we get 6 times 120. Now, 6 times 120 is 720. What's interesting is that 24 times 30 is also 720. So what that means is we have proven that when you have the LCM and you have the GCF of a group of numbers and you multiply them together, that's going to equal the product of the original two numbers. And that's exactly why the answer here is C. So, again, this is just something you want to have on the back of your hand. If you see it on the GMAT, you'll be able to answer it within seconds. To me, that's a great thing to be able to do. Okay, so what I want to do is get into one more rule, and then we're going to try to kind of bring all this full circle and do a couple more things. And give everyone about 2 minutes for this. Okay, so this is a good question. I did notice there was one C answer, and I wanted to kind of expand on why it's not C in this particular instance. So keep in mind that anytime you're given a question on the GMAT, they have to be testing something. So if in fact this problem was going to be answer choice C, we would want to ask ourselves, why would this question exist, and why would this question here also exist? Because they might as well have just said, you know, in the instance of this, what is the product of S and T? So you notice, just with the slightest little change, it says what are the unique prime factors of S and T? Well, that changes what they're looking for. And I want to go back to something really, really, really important that I mentioned about finding the least common multiple. The process was you break your value into primes, or your values, your numbers, and then you take all the higher quantity prime numbers. So that means every single prime is accounted for. So let's even talk about the LCM here of 24 and 30. If we were to break 24 and 30 down, we would see that we have a 2 to the 3 times 3 to the 1, and 30 gives us 2 to the 1, 3 to the 1, 5 to the 1. Okay, so the unique primes, well, of 24 and 30, everyone agrees are 2, 3, and 5, right? The LCM of this was 120. If we break that down, 2 to the 3, 3 to the 1, 5 to the 1, well, look at this. The unique primes are 2, 3, and 5. And again, that's because when you're getting the LCM, you're taking all of the unique primes and you're taking the higher quantities of each. So in a question like this, once again, you have this on the back of your hand, you read it through, okay, we're looking for unique prime factors. We know right away the LCM is going to give us that. Now, for those wondering about the GCF, well, the GCF does not, because we're only using the smaller quantities of what repeats. So if you have a prime factor that doesn't repeat, it's not accounted for in the GCF. So the answer here is A. Again, everyone, keep in mind, this is hard stuff. This is high-level stuff. But if you can get to a point where you know it and know it well, you will be able to get a high-level question right on the test and also save a lot of time doing it. So I want to do 2 more questions here because this is going to bring everything that we're doing full circle. There was a couple announcements I just want to make about the curriculum real quick before we head off. But I'll give everyone a couple minutes, and you can try this, and then we'll go from there. Okay, so the answer to this question is actually A. Now, the trap here, based on everything we just did, is to say that it's C, because again, if you know the GCF and the LCM of two values and you multiply them together, you know what the product is of those two values. But here's what's really interesting about this question. This is asking if m times n is divisible by 15, which really is just saying is it divisible by a 3 and a 5, right? And when you take the LCM and you break it down, you see that you end up with 2 to the 4 times 5. Now, what did we just learn about LCM? Well, we learned about the fact that LCM gives us all the unique prime factors, which means m times n is only ever going to have unique prime factors of 2 and 5. And because it's only going to have unique prime factors of 2 and 5, we know that it's never going to be divisible by a 3. So we can literally answer the question, is mn over 15 an integer? We can say 110% that the answer here is no. Statement 2, once again, we know the GCF does not give us all that we need to determine all the unique prime factors. So the answer here is A. So that's pretty cool, because that's taking a rule that's already hard and then presenting it in a way that's making it even harder from there. So real quick, I want to try to finish up one last question. This is, again, concerning these rules. So I'll give everyone about a minute or two, and then we can kind of talk about this. Okay, so given that we only have a couple minutes, and I'm sure some of you have to run back to work, we will go through this fairly quickly. Now, at a bare minimum, everyone, when you see this question and you see that you're given the LCM and you see that you're given the GCF, you know that at a bare minimum, you can multiply the GCF together and the LCM together, and you can get what MN is. So the reality is MN is 6 times 120, which is 720. Not that that matters, because we just care that we have a value. But with that, we know that we can answer, is MN over 240 an integer? The answer is yes. Now, some of you may be saying that, or asking yourselves, well, why doesn't A work here? Well, what you'll notice in statement 1 is that when we see the LCM is 120 and we see we're dividing MN by 240, we have to take into account that the unique prime factors in 120 are the same unique prime factors in 240. We didn't have that in the previous problem. In the previous problem, we had different unique prime factors between 80 and 15, which is why statement 1 worked. So in this question, just to even prove it, you could show that it doesn't work, because you could have something like MN could potentially equal 120 in statement 1, which would give us a no. Or MN could equal something like 240 in statement 1, and that would give us a yes. Now, the good news is when you're on the GMAT, and if you know this, you're not going to have to actually write these things out to prove it. You'll know to look at the unique primes. You'll understand that statement 1 or just knowing the LCM is not going to be enough. And then the beauty is you're going to fall back to the LCM GCF product rule. So I love this kind of circular motion of these questions. I think they all kind of relate to each other really, really well. And I hope that this gave everyone a sense of how the GMAT can take one rule, one formula, and then morph it into a bunch of different questions. And as you get to higher and higher levels on the GMAT, you can expect to see this type of stuff. Can't tell you that you're going to see this rule, but you will see this idea, you know, basically coming through on the test in many different circumstances. So I hope everyone had a good time today. I hope everyone enjoyed this for their lunch break. I know you could probably be doing other stuff, but we always appreciate you having here. One last note, we are in the process of adding video solutions to the example problems in the chapter lessons on our website. So we're really pumped about that. We've got about 3 chapters up worth of videos. So as you're going through the readings and if you're struggling with examples, you know, I think this would be an amazing thing for you to be able to use. And there'll be over 800 videos. So as I said, we're super pumped about it. If anyone has any questions about that or anything else, feel free to follow up with Scott or I. But we will be here next Tuesday, 12 Eastern, and I'll talk to everyone soon.